In sections 15.2 and 15.3, we studied first-order differential equations, those that were separable and those that were called linear first order. In section 15.4, we considered some second-order equations that could be reduced to a pair of first-order equations. Section 15.5 is not on our course syllabus. I wish it were. It talks about application of differential equations to Newtonian mechanics, and there's a wealth of very interesting problems that can be done. Unfortunately, we don't have the time. So the next section for us is section 15.6. 15.6, and for the rest of this chapter, talk about linear differential equations in general. 15.3, we talked about linear first order ones, and I told you I would tell you later why the adjective linear is there. I'm now prepared to do so. So let me define the definition. A linear nth order differential equation that can be expressed in the form a0 of x, meaning that's a function of x multiplied by the nth derivative of the function. Another function of x, a1 of x, multiplied by the n minus first derivative. And you keep on going until the end, in which case you get at the end a sub n minus 1 of x, function of x, dy dx, plus last function a n of x multiplied y is equal to any function of x, where a0 of x is not identically 0. Because if that were identically 0, this wouldn't be here, and the equation would not be of order n, it would be of order n minus 1. So anything that can be written in that form is said to be linear nth order. Really complicated looking thing, all right? But we'll get some simplifying notation in a moment, and then we're going to talk about how to solve that. Notice if n is equal to 1, then what do you go? Then you're really only going to have these first two terms. You're going to have a0 of x multiplying dy dx plus a1 of x multiplying y is equal to f of x. And if a0 is not equal to 0, now we don't say it can't be identically 0, right? But there could be points, like if that were x and x minus 1, that's not gone. But there, at x equals 0, it would be 0, and x equal to 1, it would be 0. Okay? So I'm saying, if you're saying we're in an interval where this not happens, we could divide and write dy dx. a1 of xy over a0 of x is equal to f of x over a0 of x. And what's that? That's the linear first order ones that we discussed in section 3. We call this p of x, and we call this q of x. And we discussed that differential equation in detail, and the nice thing about it was, we found that you can produce an integrating factor for that differential equation, and you can therefore solve it, and when you get a solution with a parameter in it, I noted there that it was general. And when you find a one-parameter family of solutions of this linear first order, it's going to be general. We're going to be able to show shortly that the same thing is true for this one. If you find me an n-parameter family of solutions, it will be general. And that is the optimum thing that we can come up with. Now, this is rather cumbersome. So I'm going to introduce notation to kind of simplify its representation so I don't have to keep writing that down all the time. Would you mind, no, first of all this, suppose we let d stand for d by dx. So big D, and there's lots of people who teach first year calculus like that notation, big D standing for derivative. And then d squared, doesn't look like d, d squared stands for the second derivative, and so on. Then if I use that notation, I can write a0 of x, d to the n y, a1 of x, d to the n minus 1 y, dot, 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 down to dy, but I need a coefficient, a sub n minus 1 of x, dy plus a sub n of x, y is equal to f of x. So that didn't simplify things tremendously. It just replaced this with dn of y. Would you allow me to do the following? Suppose I put a bracket there, and I take this out, and I take that out, I take that out, and I put the end of the bracket there. So what I want to think about is that this thing in the bracket is what I call a differential operator. It takes derivatives. So what you interpret this to mean is do this to that, which means take the derivative of y and multiply by that. Then take the n minus first derivative of that, multiply that, and add them together. So it just, pardon me, operate on this function y that follows. So we call it a differential operator. And now comes a big simplifying notation. I'm going to represent this differential operator by that. All of that I'm going to denote by that. If you look in here, what do you see? Don't say that you see A's. This is a bunch of X's. This is a bunch of X's. These all are bunches of X's, right? And so all you see in there are X's and D's, right? So then we have the nice notation, phi of X and D operating on Y is equal to f of X. So there's my nice short notation to stand for this. Let me return to this and make some comments. This is a very special form on the left-hand side as far as the y's are concerned. You can have any x's in here you want. You can have exponentials, you can have trivias, you can logs, I don't care. But the y's are there special. All you got is a function of x multiplying a y, plus a function of x multiplying a derivative, a function of x multiplying derivative, dot, 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 dot. You don't see any y's squared. They're not cubed. You don't see sine of y. You don't see y times y primed. The y's are there very nicely. All you got is a list of the function and its derivatives, and in front of those things, you can put x's, but you can't put any more y's. All right? So linear differential equations have to have that very special form. For example, for this notation, this differential equation is perhaps one of the most important equations when it comes to engineering. This one, x, y double prime plus y prime plus xy is equal to 0. It is second order, and it is linear. You got y with some x's in front of it, not too many. You got y prime, you don't have any x's in front of it. You got y double prime, you got an x in front of it. That one is linear second order. It's called Bessel's differential equation of order 0. And you cannot study heat flow, vibrations, or potential without running into Bessel's differential equation at some point. It always crops up. So it's a very important one. And it is linear. We would write for here that phi of x and d operating y is equal to 0, and the phi of x and d would be x d squared plus d plus x. Right, so that stands for this. Right? Nice, simple form. If I gave you this one, 2y double prime minus 3y prime plus 6y is equal to 10x. time, you'll notice, not like this, where you had some x's in the coefficients, there aren't any x's in front of these terms. It is linear, and it's second order. This time, I would simply write phi of d operating on y is equal to 10x. I wouldn't put any x's in here because there aren't any. So phi of d then is going to be equal to 2d squared, 3d, and 6. Hi. So all of that was simply notation because I'm lazy. Mathematicians are inherently lazy and make up symbols to stand for everything so they don't get tired of writing all the time. I'm now prepared to tell you why this differential equation that we had in the board of medical is called linear. I'm going to define an operator, so definition. An operator L on a set, say S, of functions is said to be linear if two conditions are satisfied. If for any two functions, y1 of x, but I don't need any x in there, y1 and y2 in S, and any constant C, the following two properties are true. One, that L operating on y1 plus y2 is equal to L operating on y1 plus L operating on y2. The same. If you add the functions and then operate, you would get the same thing if you operated and then added. And second property is that L operating on CY1 is the same as C, L operating on Y1. In other words, you can pull a constant, if you like, through the operator. Any operator that satisfies those conditions is said to be linear. Now you think about calculus. What are the operations that you perform in calculus? One, first operation, limits. Our limit is taking limits, a linear operator. Is the limit of a sum the sum of the limits? Can you pull a constant through a limit sum? And the answer is yes. Limiting is a linear operator. What about differentiation? Taking the derivative. Is the derivative of a sum the sum of the derivatives? Yes. Can you bypass a constant when you differentiate? Yes. What about antiderivatives? What about definite integrals? Are they linear? The answer is yes. Calculus is a linear subject. All right? That's why it's so beautiful. Does that mean everything is linear? No. It's taking the logarithm. Linear is the log of a plus b equal to log a plus log b, and the answer is no way. Is taking a sine a linear? Is the sine of a plus b equal to sine a plus sine b? No. All right? So not everything is linear. It's just the operations in calculus are, but there's lots of operations in mathematics that are not linear. Square rooting is not linear. The square root of a plus b is not the square root of a plus the square root of b. So there's lots of things that are linear, and there's lots of things that are not. Well, I ask you, in our linear differential equation, when it is phi of x and d operating on y1 plus y2 going to be the same as phi of x and d operating on y1 and phi of x and d operating on y2. Well, this is simply a differential operator. You know, it's got all kinds of derivatives in there, and differentiation is linear. So this is true. And similarly, phi of x and d operating on c times a function is going to be c after you operate on the function by phi. That will be true also. So this differential operator that we're seeing in linear differential equations is a linear operator, and therefore that's why we call this thing a linear differential equation. Because an operator is linear. We don't do a lot of theory in this course, but I think it's important that I point out a little bit about solutions of differential equations. Now, the book talks about it from the point of view of nth order differential equation. Let me simply talk about it from the point of view of a second order differential equation. Same idea, but not the same generality. Suppose I've got a second order differential equation, linear, so there's a linear second order differential equation. I'm going to assume that the following is true. That A0, A1, A2, and F are continuous. And I'm going to assume that A0 of X is not equal to 0 in some interval. Normally one talks about solutions of differential equations on intervals. We haven't done a lot of that, but if I were teaching a math course, that would be very important, the interval we're talking about. But here for us, not so important as it is for the mathematicians. So let's suppose that's true. And we've got a solution. We find a solution of this differential equation. The question is, what could we say about it as far as properties are concerned? And we know it satisfies. Suppose that y of x, suppose that y of x is a solution of this differential equation, right? Perhaps on this interval I. Well, to say it satisfies this differential equation means it has to have a first derivative. Or you couldn't satisfy this equation. Oh, it also means it's got to have a second derivative. But if a function's got a first derivative, theory in first year said the function therefore had to be continuous. Well, similarly, if it's got a second derivative, it means that the first derivative must be continuous. So if a function is satisfied this, then it has to be continuous, and it has to have a continuous first derivative. Furthermore, since this one is not 0, I could divide by it and write 1 over A0 of x, and then I'm going to solve it for this. U, over there, u divide by f of x minus A1 of x dy dx minus A2 of x times y. So if I've got a solution, then its second derivative must be equal to this. Now remember, I've assumed that's continuous, I've assumed that's continuous, I've assumed that is continuous, right? And I just concluded a minute ago that that guy had to be continuous, and that guy had to be continuous, therefore that's continuous. And then I'm dividing by this, and it's never 0. Therefore this is continuous. The second derivative is continuous now. So I'm concluding then that y prime, and y double prime are all continuous. Right? That when you solve this differential equation, assuming that these conditions are met, then you cannot have a function that's got a discontinuity. It can't jump from here up to here. It can't have a corner, because that's a place where the first derivative does not exist. And it can't have a discontinuity in the second derivative, whatever that means geometrically. Solutions of differential equations that are linear and have nice coefficients must be nice. They can't be ugly functions. Are we saying then, oh, the log function is an ugly function? Yeah, but it's nice on intervals. It's not nice if you want to talk about x equal to 0 or negative. But you want to talk x bigger than 0? That's a beautiful function. right? Absolute value function. That's a nice function, but it's got a corner here. It might be able to satisfy a differential equation if you only wanted to talk x bigger than 0. But it can't satisfy the linear differential equation between -1 and +1, because it's got a corner there, and we can't have that. So solutions to differential equations that are linear and satisfy these have to be nice. Now, if this can have discontinuities, or that could, then everything could break loose, okay? Then I can't predict anything. But when those functions are nice, then the solutions are nice. Section 15.7. Want to talk about how to solve these linear differential equations. We're going to break the discussion up into two cases. Remember, we're talking about differential equations that are linear, and then I have this representation, operator notation, that, right? But remember, when you see this, you must think what I had written on the board a long time ago, right? How ugly that was, but that's what it stands for. We're going to break discussion of this differential equation into two cases. First case, when this right-hand side is 0. That's the easier case to look at, obviously. When the more things are 0, the better. And then we'll come back after we finish that, and we'll talk about what if this is not 0. So, definition. This differential equation, phi of x and d operating on y, is said to be homogeneous. If f just isn't there. Otherwise, it is said to be non-homogeneous. Now, this is not a universal word. I've never seen dishomogeneous, but I have seen unhomogeneous and inhomogeneous. Right? I prefer the non-homogeneous, but some authors like inhomogeneous or unhomogeneous, but I've never seen dishomogeneous. Right? So we're going to study the homogeneous ones first. We're going to look at equations phi of x and d operating on y to 0. Solve those first, at least some of them. Right? And then we'll come back and talk about what do we do if it's non-homogeneous. And I'm going to illustrate the idea in a minute, but I need a theorem that is kind of, well, it takes one line to prove it. And it says the following theorem. And it's called the superposition principle. And it underlies everything we now do with this topic. It says the following. If y1 of x, y2 of x, delta ym of x are solutions of our linear, homogeneous differential equation, then so also is the function obtained by multiplying the first one by a constant, the second one by a constant, and all of them by constants, and adding those things together. In terminology in first year, when you talk about vectors, we would call this a linear combination of those. That's a linear combination of those guys there. You got a constant times 1 plus a constant times a second plus a constant times a third plus and the superposition principle says if these guys individually satisfy this differential equation so that as any linear combination whatsoever. And it takes one line to prove it. If you wanted to prove that this satisfies this differential equation, you'd plug it in and see phi of x and d. You operate on c1, y1 plus c2, y2. Let me drop the of x's. And you say, I need to prove that this is equal to 0. But this is a linear operator. And one of the properties of linear operator is that when you're going to sum of things, you can operate on them individually. So this is phi of x and d operating on c1, y1 plus phi of x and d operating on c2, y2 plus down to phi of x and d operating on cm, ym. So says that first property of linear operators. But the second property says, if you've got an operator that's linear and you operate on a constant type something, you can pull a constant out. So let me pull them out. And right that, you're gone. You are going to be out here, C2. All right, you're out. And you're out also. But then how much is this? This is phi operating on y1. But what's y1? It's a solution of this equation. So if I plug it in, I get 0. That's 0. What's this? That's 0. What's this? That's 0. So the answer is 0. And we proved it. And it took basically one line. But what we used, what was important, was that that was a linear operator. If I weren't linear, I couldn't do it. So here's why I feel this is so important. A couple examples to illustrate. I claim that y1 of x equal to e to the 4x and y2 of x equal to e to the minus 3x are solutions of the following differential equation. Now, you don't know how to solve this, but by the end of this class, almost the end of this class, if not the next one, you'll be able to solve that one almost mentally. I'm just quoting. You can check by putting this here, here, and here, and see if you get 0. Put it here, here, and here, and you'll get 0. And you will. Take my word for it, or go and check it. Right? So if those guys are solutions, then y of x equal to any constant times this one plus any constant times that one is also a solution. And what I've got now is a two-parameter family of solutions. So from these individual solutions, I now have me a two-parameter family of solutions. And that's what I would search for if I've got a second-order differential equation. I'm looking for a two-parameter family. Is it general? Yes, but we don't know that yet. Here, y1 of x equal to e to the x. Let me do e to the minus x. y2 of x equal to x e to the minus x. And y3 of x equal to x squared e to the minus x are solutions of the differential equation y triple prime, 3y double prime, 3y prime plus y is equal to 0. Again, I'll show you shortly where they come from. Right now, let me plug them in and check. I'll leave you to do that if you want. But then by the superposition principle, then y of x equal to c1 e to the minus x, c2x e to the minus x, and c3x squared e to the minus x is also a solution. It's a three-parameter family of solutions. And that's exactly what I would look for if I've got a third-order differential equation. 3 parameters. Is Is it general? Yes, but you don't know that yet. So what? Oh, we're getting the idea then. If you want to find, say you've got a fourth order differential equation, and you want to find a 4-parameter family of solutions, go find 4 solutions. Superposition will turn the 4 solutions into a 4-parameter family of solutions. So we don't go around looking for parameter families, we go around looking for individual solutions so we can superpose them to produce the parameter family. That's the beauty of this thing. We don't look for parameter families. The superposition principle produces them, provided we've got the individual solutions. But there's a problem if we're not careful. Here's the problem. If I go to that first example, this one, I know that y1 of x equal to e to d4x is a solution. Question is, let's call it y3 so we don't confuse it with that one. 10 e to d4x, is that a solution? Now you could tell me in 2 ways. 1, you could go plug it in and see. 2, you should be smarter than that. You've got a superposition principle that says if you put a constant in front of any known solution, it's still a solution. So those are both solutions. If I superpose them, I put a c1 e to d4x plus 10 c2 e to d4x. Do I have a 2-parameter family of solutions? And the answer is no. You could factor out the e to the 4x. And you could call this thing, that's a constant, call it c3. So you do not have a 2-parameter family. So you can't use these 2 to produce the 2-parameter family. My second example over there. I know that y1 of x is equal to e minus x. I know that solution. I know that y2 of x is equal to x, e to the minus x. I'm going to ask, what about this? 5 e to the minus x plus 2 e to the x, e to the minus x. Is that a solution? Superposition says, yes, it is a combination of these 2, therefore it's a solution. If I superpose them, c1 e to the minus x, c2 x e to the minus x, and c3 times 5 e to the minus x plus 2x e to the minus x. Do I have a 3-parameter family of solutions? And the answer is no. I could group these 2 and write c1 plus 5c3 e to the minus x, and I could group the other 2 and write c2 plus 2 c3 x e to the minus x. Call this c4, call this c5, and you've only got 2 parameters. So I cannot superpose these 3 and get me my 3-parameter family of solutions. Now, what I want you to sit back and think about is answer the following question. Why does superposing these work? Why does superposing these work? Why does superposing these not work? Why does superposing these not work? What's the difference? Because we want to know. What do functions have to, what do solutions have to look like? So that if we superpose them, we get the number of parameters we want. What's the difference? Well, here you've got to say to yourself, this is 10 times that one. That's why it didn't work. What about this one? Well, you can say the same kind of thing, that this one is 5 times that one plus 10 times that one. And indeed, that's right. This one is not some number times that one. And none of these is any, you can't say take this one is equal to something times that plus something times that. Or this is something times that plus something times that, meaning constant. Constant times this, constant times that equal that. No, you cannot find constants like that. Now you have seen this idea before in first year. You saw it in the context of vectors. What were you talking about? When you said in first year, this vector could be written in terms of those vectors. And you also said, this vector, or I've got these vectors here, and none of them can be written in terms of the others. What were you talking about? And you were talking about linearly independent and linearly dependent sets of vectors. We're going to use exactly the same terminology here. If one solution of we're talking about linear, so maybe I emphasize that, linear differential equation, is a linear combination of the others, the set of solutions is said to be linearly dependent. If any one of them can be written as a combination of the others, that means one of them can be written constant times that, plus a constant times another one, plus a constant times another one. If you can do that, then solutions are said to be linearly dependent. If no solution can be written in terms of the others, the set of solutions is said to be linearly independent. So this is not a new concept to you. It's simply now in terms of solutions to differential equations as opposed to vectors that you had in 1210. Right? In fact, if there's an advanced mathematical course on differential equation, I would talk about a vector space of solutions. So the vectors would actually be solutions. But we're not there. We don't know to do it in that kind of formality. But we've got the same terminology. So now what we can say is the following. The following theorem now follows. Theorem. If n linearly independent solutions of phi of x and d operating y is equal to 0, a linear, nth order, homogeneous differential equation. If are superposed, an n parameter family of solutions is obtained. So as long as the individual solutions are linearly independent, you're going to get an n parameter family. Clear? Furthermore, as a corollary, the n parameter family of solutions talking about this up here, is a general solution. But if you take n linearly independent solutions, you superpose them, you get an n-parameter family of solutions, and it will be general. All solutions are there. There can't be any more. This is the optimum result. But remember, we're talking about a linear, homogeneous differential equation. We're not talking about any sort of differential equation. It's got to be linear, and it's got to be homogeneous. All right? Example. Find a general solution for y double prime 9y is equal to 0. There. That's linear. That's homogeneous. It's also particularly simple in that I don't have any x's here and I don't have any x's there. In fact, you can look at that and you can guess two solutions. You need functions so that when you differentiate them, you get minus 9 times what you started with. So search your memory and say, what functions do I know of? If I differentiate it twice, I basically get it back again, and maybe I can fix up the 9. What's got to come to mind is sines and cosines. If I differentiate sine x twice, I get minus sine x. But I want a 9. How about I take sine 3x? Right? Isn't y1 of x equal to sine 3x a solution? And y2 of x equal to the cosine of 3x is also a solution. And therefore, a general solution is y of x equals some constant sine 3x plus any constant c2 be cosine of 3x. There's a general solution. Simply because we were smart enough to spot two solutions. If you, for instance, were to put x in here, now I got a big problem. I have a huge problem in trying to produce two solutions. If I wanted to do that, that's math 3. That's what you're going to do backwards. All right? So they're not always easy to find these individual solutions. But we've got the idea. Right? The superposition, what it's doing for us, it's saying, if you can find individual, linearly independent solutions, then you can superpose them, and you've got yourself a general solution. Now, there is a nice mathematical way to determine whether a set of solutions is linearly independent or not. And it involves what are called Wronskins, and they're discussed in the exercises. And sometimes they are necessary. In Math 3, there would be a problem where I would need that Wronskin stuff. For us, and the kind of functions we're going to see, and the solutions we're going to see, I can look at them and say, none of you guys can be written in terms of the other people, therefore you're linear independent. Or you're 5 times this and 10 times him, therefore these guys are linearly dependent. Anything that we're going to see in this course, it is clear whether they're independent or not. But do realize, that's not satisfactory to a mathematician. He wants a test, and the Wronskin is the way to do it, and it is necessary in some discussions, but it won't be for us. Section 15.8 talks about, still we're talking about homogeneous. So the objective is to find these linearly independent solutions so we can superpose. If we do something like this, if x's are here, if those coefficients, which in general, to now could have x's in them, if those x's are there, it becomes an extremely difficult problem to find solutions. And Math 3 does that for some problems. We can't. The only ones that we're going to talk about are when these coefficients are numbers. Like those two examples I had a minute ago. I had one here, second order. I had one here, third order. Coefficients there were constants. I was able to kind of spot solutions, and you will be able to do that shortly too. So that's what we're now going to look at. We're going to look at linear, nth order, homogeneous, constant coefficient differential equations, which means I would write them this way. Right? There's the homogeneous. You got the phi guy saying linear, and you got no x's in here, which is saying constant coefficients. All right? So that's the ones we want to concentrate on. And we will be able to solve all of these, at least theoretically. Right? You might say, well, that's really highly restricted. Pardon me. You're not allowing any x's in these coefficients at all. And I agree. But there are huge numbers of applications of this kind. And we're going to see some at the end of this chapter when we discuss vibrating mass spring systems and LCR circuits. They fall into this category. So it's not so restrictive that there's no examples out there. There's a multitude of them. All right, I'm going to illustrate the idea of how we do it by considering 3 examples. And here's the first. Y double prime minus 2y prime minus 15y is equal to 0. All 3 are going to be linear, homogeneous, constant coefficient, and they're all going to be second order. I'm going to solve them all right? But I'm going to state results because I think results will be clearer if it were a third order or a fourth order, whatever order, based upon these 3 examples. So the examples will be simple, and then we'll generalize. So here's our first one, is find ourselves 2 individual solutions of that differential equation so that we can superpose them, provided they're independent, and get ourselves a general solution. Well, look at it from the following point of view. If I took this one over there, and I took this one over there, I'm looking for functions whose second derivative is twice the first plus 15 times itself. And I rack my brain, and I say, what kind of functions would do that? Would x squareds do that? Polynomials do that? And the answer is no. Polynomials don't do that. All right? What else? Well, I might think of logarithms, but I don't want to go too ugly. No, I don't think logarithms would work either, okay? Because you differentiate logarithms, you'd have a log here, and you have non-logs here, and therefore, that's not going to work. Well, what next then? Well, I probably would think either of trig-e's, because they kind of reproduce themselves, or exponentials. I'm going to try exponentials. I'm going to try y equal to an exponential, all right, x. But I don't know exactly what to put here. But I think this might work. So what I'll put here is an m, and I'll see whether there's an m that I can put here so that this will satisfy this. If I succeed, great. If I don't succeed, I'll try something else. But this is based, I think, on reasonably intelligent guessing. So let's try. So if we substitute, what do we get? We want this to be a solution, then it's got to satisfy. Differentiate it twice. M squared e to the mx minus 2m e to the mx, and then minus 15 e to the mx must be 0. If this is to satisfy this, then this has got to be satisfied. But you'll notice there's an e to the mx in every term. Let's get rid of it. Divide it out. It can't be 0. So now we're at the stage is this is a solution of this if m satisfies. That's a quadratic equation. Factors m minus 5 and m plus 3 equals 0. And therefore, m is equal to 5 or minus 3. Therefore, y1 of x equal e to the 5x is a solution, and y2 of x equal to e to the minus 3x is a solution, and those guys are linearly independent. There's no way this is a number times that. Therefore, a general solution is y of x is equal to constant times the first plus a constant times the second. So that worked very well. All right? Very well. Well, let's try another one. I have another one here. Y double prime, 6y prime, plus 9y is equal to 0. Well, since that works so well over there, I think I would try it again. So let's try y is equal to e to the mx. Substituting m squared, e to the mx. 6, m e to the mx. 9, e to the mx equals 0. Get rid of the e to the mx's. M squared, 6m plus 9 equals 0. Oh, it factors again. Uh-oh. I'm only going to get one solution with, in terms of tall 10, multiplicity 2. And so all we get then is one solution, e to the minus 3x. And we don't have a second one. Darn. It didn't work. So I've got to find another solution. So now I'm going to rack my brain again and say, what else could I conceive of that would satisfy that besides that? Am I going to try something extremely new? And I don't like that idea. I've got an idea. Let's try the following. Try y2 of x is equal to some function of x times this guy. Right? I don't really want to abandon the exponential, so maybe I could find some function to put here so that that satisfies as well. If I find something good, if I don't, give it up and try something else. So let's substitute. So if we substitute, we've got to take the second derivative of this. How do you take the second derivative of a product? It should have been shown a nice way to do that in first year, but if you weren't, let's go off to the side here. If you want uv prime, double prime, right? You could say, I'm going to use a product rule to get this, and then I'll have two terms, and then I'll use two product rules to get that. Don't do that. This idea of differentiating a product multiple times comes up a lot in our discussions. So learn a better way. The better way is that this is u double prime v to u prime v prime and u v double prime. Differentiate the first twice, multiply by twice the first derivative of each, and then him times the second derivative. Is it looking familiar? That should kind of ring a bell. What do you think it would be if it was a third derivative, if it rings a bell to you? How about u triple v, 3 u double 1v, 3 1u vw, and u v triple? The answer is yes it is. All right, yes it is. Okay. Remember those. Those are very useful. So let's use that on here. So we need the second derivative, which means v double primed e to the minus 3x. Second of him times him. Then we need twice the first derivative of each. How about minus n? 6 v prime e to the minus 3x. Then we need this one times 2 of him. All right? That means 9v e to the minus 3x. How does that work then for second derivative of him? Then we need 6 times first derivative, v prime, e to the minus 3x, minus 3v e to the minus 3x. And then we need 9v e to the minus 3x. And that's supposed to be equal to 0. Looking complicated, but take a look. Notice that one and that one. They're the same. Cancel, cancel. Take a look at this one, and this one. Here you got minus 18, here you got plus 9, and here you got plus 9. Ding, ding, ding. What are you left with? The only thing that's left is this. And that can't be 0. Therefore, p double prime is equal to 0. But what are functions that you differentiate them twice, you get 0? Well, integrate them twice. Doesn't that say that v is equal to some constant times x plus some constant? So we're saying here, you put that there, pardon me, and you got yourself a solution. Oh my God! Notice, if I pick that up and I put it here, I'm going to have a 2-parameter family. I guess I'm done. That's not what I was searching for. I was searching for another one. Okay? So let's back up a little bit. Well, I could do that. That would be fast. Okay? Suppose I put A equal to 1 and I put B equal to 0. What does this turn into? That turns into x, and then v then is equal to x e to the minus 3x. There's the second solution I was looking for. Notice if I put A equal to 0 and I put B equal to 1, what do I get? That V is equal to 1. What have I got? I got my first solution back again. Right? So this is the one that I was really looking for. And if I took that one, and I took this one, and I superposed them, I would get a general solution. But if I pick that up and put it there, I get it faster. But the key is that I did find a second solution by doing this. So there's 2 examples, and I've got one more. That's going to bother you somewhat. At least it does most people. And I have to get you over the hurdle. So this one is 6 and 13. Y double prime plus 6y prime plus 13y is equal to 0. Again, second order, linear, homogeneous, constant coefficients. Let's try what we did before. Try y is equal to e to the mx. M squared, e to the mx. 6m, e to the mx. 13, e to the mx equal to 0. Cancel the e to the mx. M squared, 6m, 13 equal to 0. Quadratic again. But it doesn't factor. So I have to pull out my quadratic formula. Minus b, plus or minus, square root, b squared, 36, minus 4ac, 52, all over 2a, 2, minus 3, plus or minus. That's minus 16. Oh, we're getting complex, right? Okay, but would that be then plus or minus 2i? You get a 16, you take the square root, you get a 4, divide by the 2 at the bottom, 2i. So we seem to have fallen flat in our face this time. What we're saying is the following. We're saying there's no real number that you could put here and have this satisfy that. But we are saying, if you pick one of these up and you put it here, you will have a solution to this. And you put the other one up there, you will have a solution. But they won't be real solutions. And I am looking for real solutions. But I'm kind of dumb. I'm going to put them up there anyway, okay? So I'm going to say that here's two solutions. y1 of x equal to e to the 2 minus 3 plus 2i times x, and y2 of x equal to e to the minus 3 minus 2i of x. These guys are solutions. They're just not the kind that I want. I want real people. Well, I'm going to still plug away and say, therefore, my superposition so also is the function y of x being some constant times the first one plus some constant times the second one. But again, it's complex. But you had something in first year. You dealt with these kinds of things in first year, these complex exponentials. Would it be okay if I broke this into e to the minus 3x times e to the 2ix? And do the same thing over here. E to the minus 3x times e to the minus 2ix. Both of them have an e to the minus 3x. Let me pull that out. E to the minus 3x. Leaving me then c1 e to the 2xi, c2 e to the minus 2xi. Are you happy with that? And remember in first year when you studied complex numbers, you had this thing called Euler's identity that I could apply to those exponentials. So let's do that. We would have them. Y of x is equal to e to the negative 3x, c1 cos 2x plus I sine 2x. That's what Euler's identity said for e to the 2xi, plus c2 cos should be cos minus 2x. But the cos of minus is the same as cos of. Then I should have here the sine of minus 2x, but I could pull that minus sign out and put it here. So sine 2x times I, and finish. Right? I still don't know what I'm doing, but I'm doing it, okay? I still got all this complex stuff in here that I don't like. All right, well, since I put this I out front here, let me put this one up in front too, so we don't get confused. All right, I propose now to take these things inside here and group the two cosine terms together and group together the two sine terms together. So I would have c1 plus c2, the cosine of 2x, plus I and c1 minus c2 sine 2x. There. Right? Now I'm going to pull a fast one. I'm going to say, I'm going to call that c3. I'm going to call this c4. And therefore, e to the minus 3x, c3 cosine 3x. Oops, not 3, 2. Plus c4 sine 2x. Isn't that pretty? There's my solution. There's my general solution. It's got two arbitrary constants in it. And what are you going to say to me? You're going to say, but you're hiding the I. It's still in here. Well, it could be, but it might not be, all right? Let me show you why it doesn't have to be. Now, what were C1 and C2? C1 and C2 at this point were any constants whatsoever. I kind of was thinking about them being real, but since this is complex and this is complex, C1 and C2 may be complex too. Suppose I put C1 equal to A plus BI, and I put C2 equal to A minus BI, where A and B are any two real numbers whatsoever, all right? Now what then is C3? C3 is supposed to be those two guys added together. That's 2A. What is this supposed to be? I times C1 minus C2 is I times this one minus that one. This one, that's 2BI. Ooh, which is minus 2. This is 2B. And that's a real. And that's a real. And that A and B can be any two reals whatsoever. I didn't specify what they were. So in other words, I can look at this thing and say, for any real number here, any real number here, this is going to satisfy this differential equation. Therefore, I got me a two-parameter family. Therefore, I got my general solution. So I succeeded. All right? By wading myself through all that complex stuff, I eventually produced a two-parameter real family of solutions. All right? I'm going to leave that for this video because now we want to say, what do we see common among these three examples that we could now use for other examples? So that will be in the next video.